All right, welcome back. In this video, we're just going to do a short video on how to write Lewis structures for polyatomic ions. Kind of left that out. I just wanted to focus on that all by itself in this video. And if you didn't watch the video for how to write Lewis structures on covalent compounds to begin with, you might want to watch that one first. So just this 10 point, that's just 10.5. Very important video, very important concept that you know how to do covalent structures. However, if you haven't watched that video, you could probably get away with, if you're a quick learner, watching this video, and it's pretty much the same process with just one addition. So I'm basically doing everything that we've done so far, but I'm just adding one little extra component. And so I'll do a thorough review of how to write Lewis structures for covalent compounds to begin with, as the whole process, so the steps will be the same. And so this could even be a learning video for you if you haven't looked at 10.5 yet, but follow with me here in your book to 10.5. After all these steps that you'll see here, after these examples that we did last time, you'll see writing Lewis structures for polyatomic ions. Well, if you remember, polyatomic ions are groups of elements. That's what polyatomic means. Groups of atoms that come together that in and of themselves are a covalent compound, but overall they have a charge, and we can use those to make ionic compounds. Like you can have, if you just pull out your list of polyatomic ions, if you still have it, or you Google it, you'll see there's like nitrate, sulfate, phosphate. Usually they have oxygen, like PO4, NO3. Those compounds literally act as ions. So you can have like sodium nitrate, potassium nitrate, magnesium nitrate. Okay, you can put a metal with a lot of those polyatomic ions. Remember, most of the polyatomic ions have a negative charge. It's only ammonium that has the positive charge. There's a whole list, though, that have a negative charge. What does that mean? What does that negative charge mean? What does it come from? Well, it literally comes from having an extra electron. The whole structure has an extra electron, and so that's what we're going to have to do when we write Lewis structures, is consider that extra electron. So if we look at a simple one here, I think this is a cyanide. It's carbon and nitrogen, but yet it acts as a polyatomic ion with a -1 charge. So you could have like sodium cyanide, for example, because sodium's +1, cyanide's -1, so that could be an ionic compound. But if you just want to look at this polyatomic ion, cyanide, here's what you'd have to do. Remember, you're first going to calculate how many valence electrons are you dealing with, how many are you working with. Well, the formula is just Cn, so how many valence electrons does carbon have? 4. How many does nitrogen have? 5. So 4 plus 5 is 9, but we need to add one more because cyanide has a negative charge. Cyanide has a negative charge. I mean, you'll see that here. I don't know why they don't have that negative symbol there, but if you're writing a Lewis structure for the Cn minus ion, that minus means you've got one extra electron. So overall, we need to show 10 electrons. So how do we show those? Again, I want to do a thorough explanation here. You're first going to show your bonding pair. Step 1 is to write a skeletal structure. Well, do you have any other option for skeletal structures than putting carbon right next to nitrogen? No. You could have carbon on top, you could have carbon to the right, it doesn't matter. As long as you have a carbon right next to a nitrogen, you're good. Okay, step 2 is to show the bonding pairs. So we need to show a pair of electrons right there that are the bonding pair for carbon and nitrogen. So that's the only bonding pair we have, so we're going to put that one first. And then the next step is to distribute the remaining electrons to all the terminal atoms, giving them octets if you can. So do your best to give everything an octet. And what you're going to run into is this situation here. In fact, both of these are terminal atoms, aren't they? Because since we're only dealing with 2 atoms, I'll show you a more complicated example in a minute. But and this is what you're going to run into. You're going to show 2, 4, 6, 8, 10 electrons used, but not everything's got an octet, does it? Both the carbon and the nitrogen need 2 more electrons apiece to get an octet. Well, please don't ever add electrons I know it's tempting, but you cannot do that. You can't just put electrons here. So how do you fix the problem? You have to borrow. You have to borrow. Step 4, it is, if any atoms lack an octet, then you can borrow electrons and form double or triple bonds as necessary so that you can give everything an octet. And we are going to form a triple bond. That'll be fun. The way we're going to do that is we're going to borrow 2 electrons from the carbon. We'll put them here. And what you want to do is you want to, how do I say this? You want everything to be kind of as balanced as possible. And so just like there's some symmetry in a lot of skeletal structures, like you have some symmetry here with nitrogen and the hydrogen spacing themselves out as far as possible from each other. And the same when you go to borrow electrons, if we're going to end up borrowing 2 here and 2 from somewhere else, let's borrow from 2 from over here. So we're going to borrow first of all 2 from the nitrogen, from this carbon, so that we have a double bond. But then don't borrow the next 2 from this carbon. In fact, you would see that you can't even do that. You can't do that, can you? Technically, you could do that. Yeah, you could borrow these 2 from the carbon as well, and you'd still have a triple bond there. But no, yeah, but it still wouldn't have an octet. So no, you have no other choice but to borrow the next 2 from the nitrogen. Then everything's got an octet. And if you don't believe me, remember all you got to do is put a circle around the element and the electrons around the element. So if we were to put an imaginary circle here and we count, we got 2, 4, 6, 8. If we do the same thing for the nitrogen, we put a circle around the element and all the electrons around the element, then we can count 2, 4, 6, 8. So we got octets for both. So both the nitrogen and carbon are happy with their octets, but we have a triple bond here, don't we? Because we have 3 pairs of electrons. So replace the pairs of electrons with lines so it doesn't look silly, because that technically you don't see a whole lot of structures written like that. Usually you see lines. Remembering that each line represents a bonding pair. Lone pairs are still shown as dots. So we see the carbon's got a lone pair, the nitrogen's got a lone pair. But if you're actually to count electrons, you got 2, 4, 6, 8, 10 electrons. But how many protons do we have? Well, carbon's got 4 protons, nitrogen's got 5, so that's only 9 protons. So since you have 1 more electron than protons, overall, this structure has a negative charge. And so that's what makes it a polyatomic ion. All right, it has to do with the tendency or the urge for this compound to have octets. All right, the octet rule is a very valid rule. Okay, let's look at another example here. Again, this is the famous only positive example. The only positive polyatomic ion that we really deal with is ammonium. Why is it positive? Let's look at the Lewis structure, and it'll help us to do that. We first begin by writing a skeletal structure, remembering that number 1, you need some symmetry, so this would be the only really symmetrical way to draw this. But also, and you want to space everything out as far as possible, so like these hydrogens need to be as far away from each other as possible. So you have a north, south, east, and a west. Another thing to remember, and that would help you get this right, is that hydrogens always have to be on the outside. So there's no way you could put hydrogen in the middle, because remember, hydrogens form duets. They don't have the ability to have 8 electrons around them, so they always need to be on the outside. All right. And so again, let's do our calculation first. How many electrons are we going to get to work with? Nitrogen's got 5. Hydrogens have 1, so we got 9. But we're dealing with a positively charged ion, so that means overall we're going to be like missing an electron. So let's do that subtraction real quick, and now we have 8. So we can only show 8 electrons in our structure. The next step is to place electrons everywhere you have a bond. So anytime you have a pair of atoms next to each other, that's where you're going to put some electrons to show those bonds. Okay, and then, but look there, we've shown all of our electrons. That's going to end up taking all 8 of our electrons. And lo and behold, nitrogen has an octet, and all the hydrogens have their duets. So everything is happy, right? Everything is happy. Where would you put the 9th electron? Right? You'd have no really place to put it. So that's why ammonium likes to have a positive charge. If this compound was to be stable like you see it, it's going to have a positive charge. Then it's going to be attracted to anything negative. So you're going to have ammonium chloride, ammonium fluoride, ammonium bromide, ammonium iodide, ammonium nitride, ammonium oxide. You can have ammonium with any other negatively charged, or you can even have ammonium with another polyatomic, so like ammonium phosphate, ammonium nitrate, ammonium sulfate, and so on. Don't forget to put brackets around it, and I like the lines a lot better than that. So okay, in the same video I want to address some exceptions. So there are a few exceptions to the octet rule, and so it's often good and correct in its predictions, but again, exceptions exist. So we're just going to go over those, and so when you encounter them on the test or in your homework, you will know that we're talking about the exceptions. There's actually a few more exceptions than you see here, but these are the main exceptions that you'll see. First of all, nitrogen doesn't always have an octet. Nitrogen does not always have an octet, and so and you can see that here. What if you were to write a Lewis structure for nitrogen monoxide? You would have 5 plus 6, that's 11 electrons to show. So 2, 4, 6, 8, 10, 11 electrons. Remember, you first show your bonding pair in the middle, and then you do the terminal atoms, and then you would try to make a double bond there from the oxygen to help fill that, or actually you'd probably borrow that from the nitrogen, right? 2, 4, and then 5. You would borrow these 2 from the nitrogen, put them there for a double bond. That makes the oxygen happy, but nitrogen is still not happy. It's got 2, 4, 6, 7. So what are you going to do? Add another electron and make it a polyatomic? Well, you could, but what about this compound, which totally exists? There's totally a compound called nitrogen monoxide that does not have a charge. So what's happening? Well, it just doesn't have an octet. This literally is legit. This is how the structure looks. This is actually what it looks like. And so it does exist. And why? Again, Lewis theory is not quite sophisticated enough to describe everything that's going on here. We have to remember that these electrons are actually not even particles. They're like waves. And so this stuff gets way deeper than we are trying to talk about it here. But this still works. This still works, and can still be used to make predictions about this molecule. And so we're still sticking with electron dot diagrams and these ball and stick models that we're going to use, and so all this stuff is applicable. Quantum mechanics is the real deal story, though, but it's just very confusing, and I don't know how relevant it is when all this stuff works for us right away anyways. So another exception to the octet rule would be boron. Boron can typically be happy with only 6 rather than 8. So boron trifluoride and boron trihydride is how you would say that, because those are both nonmetals, so I need to use prefixes. So boron trifluoride or boron trihydride are totally legit molecules. Those are molecules that you would see, and just don't worry about the fact that you would like to have 2 electrons there. Don't add them and make it a polyatomic. Don't do that. Just leave it how it is if it's boron. And nitrogen and sulfur. Actually, sulfur and phosphorus are 2 that can have more than 8. Sulfur and phosphorus can have more than 8. So you can see here you got 2, 4, 6, 8, 10, 12 electrons around sulfur. And here you got 2, 4, 6, 8, 10 electrons around phosphorus. And so sulfur hexafluoride and phosphorus pentachloride are molecules that are, they have expanded octets is the technical term. Expanded octets can form for actually any of the elements that are past period 3. And it's really because of the d orbitals, the d block. So all the transition metals, you'll see they're the ones that I said aren't really in this list, but they can do some funny stuff too. So a lot of exceptions occur because of the d subshell. And so because of that funny feeling there and the d block, sometimes, then anything in row 3 or on, anything in period 3 or on can sometimes meet this exception. But sulfur and phosphorus are possible as well. Okay, so again, I think that's it. The next video is going to be about resonance. This is a good one here too. So, and it's still going to make us use this skill. So it'll be a nice refresher on how to write a Lewis dot structure. So make sure though you're strong in writing Lewis dot structures before you start watching this video. Thank you for watching. We'll see you in the next one.